So for the rest of this video, the thing that we're going to be working on is if we have a function over a closed bounded interval that of course is a real valued function, and this function is continuous everywhere over that interval, then actually it does obey the uniform continuity property over that closed bounded interval. So these then are examples of functions that do obey the uniform continuity property. Any function that is continuous everywhere over a closed bounded interval is also going to be uniformly continuous over that closed bounded interval, and we're going to spend the rest of the video proving that. Now, just before we do start that, one of the things you might be wondering is, what is the point of uniform continuity? That, I think, is the reason that people often struggle with this topic, because always in maths it's very difficult to understand something if you don't understand what the point of it is. You might be able to understand this definition, but if you don't understand the point of it, your brain isn't going to attach much salience to it, much importance to it, and therefore isn't going to put much effort into remembering it. Now, I'm not going to give a detailed answer of the point of the definition of uniform continuity here, but what I will say is we will use this property in the future in proofs, and in fact the first place I think that we will use it is when we come on to study the formal theory of integration. So we will study Riemann integration, which is one of the formal definitions for integral calculus, and when we do that we will find that any function in fact that is continuous over a closed bounded interval, like these functions here that I've just written down, they are in fact Riemann integrable over their domain, the interval. And to prove that, we will have to do some work when we study Riemann integration, but in that proof, it is far easier to prove that if it obeys the uniform continuity property, that it then implies that it's going to be Riemann integrable. So in fact, by proving that these functions that are continuous everywhere over the domain, which is an interval, are uniformly continuous over that interval, then we will have effectively done a huge amount of the work that we will need later when we study Riemann integration. From the fact that it's uniformly continuous, it then follows really simply that the function is Riemann integrable. So we're actually doing some of the work that will help us later in more complicated proofs. So uniform continuity, really, it's a stepping stone for proving things about continuous functions. So let's now prove this theorem then. So we have a function defined over the closed bounded interval AB that's a real valued function, and we're assuming that it is continuous over that entire interval, and we want to prove that it's going to be uniformly continuous over that interval. Now, to do this, let's just re-examine this definition up here, because in fact there is a different way of looking at this definition. So far, the way that we've been interpreting this definition is that there is a delta that works for every single p in the domain. So if you look at every single one of the points p in the domain, that if you look at the points that are within delta closeness of p, then their image points are within epsilon closeness of one another. Now, I want to actually just rename these points p and x. So I'm going to actually rename this point p here x1, and this point here x2, and then we'll have, for all x1 and x2 that are in the domain, such that the difference between x1 and x2 is less than delta, then the difference between their image points is less than epsilon. And this is just another way of looking at what this definition is saying. So I'll write this out. So here it is now written out in terms of x1 and x2. So for all epsilon greater than 0, there exists a delta greater than 0 such that for all points in the domain x1 and x2, such that the difference between them, the modulus of their difference, is less than delta. So if they're closer to one another than this amount delta, then if you look at their two image points, f of x1 and f of x2, they are within epsilon closeness of one another. So what this is saying then is that no matter how close you want to be, you can find another closeness, a delta, such that if you take any 2 points, x1 and x2 in the domain, that are close enough to each other, they're closer than this amount delta, so the gap between them is less than delta, then it will be the case that the difference between their image points, the difference between f of x1 and f of x2, will be less than epsilon. So that's another way of looking at this definition, that there is this value delta such that any 2 points that you pick in the domain that are closer enough to each other, i.e. the modulus of their difference is less than delta, then if you look at the difference between their image points, the modulus of the difference between their image points, they'll be within epsilon closeness of each other. So that's another but equivalent way of looking at this definition. Rather than looking at one of the points as being the point P and one of the points as being the point X that's within delta closeness of P, instead this kind of makes the 2 points on an equal footing instead, and it's just saying as long as the 2 points are less than delta difference apart, then the difference between their image points is guaranteed to be less than epsilon if this definition holds true. So let's now turn on to our proof. So we want to prove that these functions that are continuous everywhere over this interval are going to be uniformly continuous over this interval. Now, the way we're going to do this is by contradiction. So we're going to assume that they are not uniformly continuous and arrive at a contradiction. So if they're not uniformly continuous, then they're not going to obey this criterion here. And that's why I've looked at this criterion in this second way, because actually this one's easier to work with. This way of looking at things is easier to work with than this initial way. So let's assume then now that this doesn't hold true for our function f. So we now get to negate this great big statement. What fun, negating all of these logical quantifiers. So the negation then of for all epsilon greater than 0, this holds true, is that there exists some epsilon that is greater than 0 for which this doesn't hold true. So there exists an epsilon, and we'll call that specific epsilon epsilon bar, and it of course is going to be greater than 0 such that the opposite of this now holds true. So there doesn't exist a delta for this epsilon bar. So instead it's the case that for all delta greater than 0, this doesn't hold true, because there doesn't exist one for which this does hold true. So for all delta greater than 0, now the opposite of this holds true. So this is saying that every single point in the every single 2 points rather in the domain where they are closer distance to one another than delta, if you look at the modulus of the difference between their image points, it's less than epsilon. So the opposite of that is that there exists 2 points in the domain x1 and x2 which are close enough to each other, so they are within delta closeness of one another. X1 minus x2 mod of that is less than delta. But now, if you look at the difference between their image points, so the modulus of f of x1 minus f of x2, it's not less than epsilon. Instead, it's going to be greater than or equal to epsilon. So that is the negation of this statement. So if this is not true, then this is instead true. So I've made just a small correction here. I had missed the bar on top of the epsilon here, so it should be epsilon bar there, that the difference between these 2 image points is going to be greater than or equal to epsilon bar, our specific value of epsilon for which this holds true. So how then are we going to find a contradiction from the fact that this is true then? So let's just look at this. For our epsilon bar value, it is the case that for all delta, no matter how small they can get really, really close to 0, in fact indefinitely close to 0. For absolutely all of them, you will be able to find 2 points in the domain that are within that delta closeness of one another, so they're closer to each other than this value delta, and yet the difference between their image points is greater than or equal to this value epsilon bar. Now, does that seem very likely for our types of functions? Remember, the functions we are dealing with are these functions that are continuous everywhere on a closed bounded interval. Now, intuitively, what that means is that you can draw them by putting your pen here and then going on the piece of paper and then going all the way to the final point here, and you never have to take your pen off the piece of paper. Now, if you think back to that counterexample that we had in the previous part the function 1 over x that didn't obey uniform continuity. So of course that function does obey this criterion that we've written down here, but the reason that that function was able to obey this criterion is because it had that asymptote. It had that bit where the graph was getting indefinitely steep, steeper and steeper and steeper, indefinitely steep, and that was the reason that no matter how small you made delta, you would be able to find 2 points that were within delta closeness of one another in the domain, and yet their image points would be further apart, or the distance between their image points would be greater than or equal to epsilon bar. In these functions, however, you're not going to be able to ever have one of these indefinitely steep asymptotes, because if you had one of those, you wouldn't be able to draw it in this intuitive way that is how you're going to be able to draw these functions that are continuous over a closed bounded interval. That's the key difference between it being continuous everywhere over a closed bounded interval and it being continuous over an open interval. Previously it was the open interval 0, 1, so it wasn't continuous at the point 0. Indeed, the function wasn't even defined at the point 0. So continuous over a closed interval is very different to being continuous over an open interval. So I hope you can sort of appreciate that these beautiful functions are not going to obey this horrible criterion, but what we now need to do is formally prove that. So the way we're going to do this is we're going to let delta get smaller and smaller, and for each of these smaller and smaller delta values, we will find 2 points in the domain such that they are within that delta distance of one another, but their image points are a distance apart greater than or equal to epsilon bar. And we're going to construct sequences out of these points. And of course, because we're going to let the delta get smaller and smaller, the points, the paired terms in these two sequences are going to get closer and closer and closer to one another. And we're going to be able to use these sequences to derive some nonsense. So we'll start actually with setting delta equal to 1. So we've got our epsilon bar that is set, and now it's the case that for every single delta you pick, that this will hold true. So we've started with a delta equal to 1. So for delta equal to 1, it is possible to find 2 points, x1 and x2, inside our domain, which is this closed bounded interval AB, such that the distance between them is less than 1, but the difference between their image points is greater than or equal to epsilon bar. Now, for the sake of my sequences looking nice and having a nice notation, I'm going to actually rename these points x1 and y1. One of them is going to be called an x value and one is going to be called a y value. So I'm just changing the symbols, and because they're referring to the delta equal to 1, they've got the subscript 1. So what you can imagine is instead of calling them x1 and x2, I've now called them x and y, and now the subscript isn't denoting the same thing as the subscript here was denoting. Instead, the value x, the letters x and y are denoting the two different values from here. Instead, the subscript is denoting the fact that they came from delta equal to 1. And the next ones are going to be x2 and y2, and they're going to come from delta equal to a half, etc. So these two values then that are forming the first terms of my two sequences, this is going to be one sequence and this is going to be the other, they are a distance apart less than 1, and I've written down here also that their image points are a distance apart greater than or equal to epsilon bar. So to find the next terms along in my sequence that I'm constructing, I'm going to go to delta equals a half. So each time I go to the next term, I'm going to half the size of the delta so that it gets smaller and smaller and smaller. So I'm going to delta is equal to a half now. And again, for all delta, this is true. So for delta is equal to a half, it's true. So for delta is equal to a half, there will exist an x1 and an x2, which we're now calling x and y. That are within our domains, they're in this closed bounded interval AB, such that the distance between them is less than delta, so less than a half, but the difference between their image points, the modulus of the difference, is greater than or equal to epsilon bar. So this is going to hold true again. So if we turned this to x2 and y2, it's still going to hold true. In fact, we could change these 1s to i's because it's actually going to hold true for all the terms of my sequence. and you go on. So I've made a few changes here. I've just put in x and y here to remind us that we're not calling them these anymore. We're calling them x and y, and of course the changes need to really be put into these as well, but I'll leave that to your imagination. I've also changed these to I because they are going to hold true for all of the ith terms of these sequences. So the next terms along, the third terms in our sequences, we're going to go to delta is equal to a quarter, so we're halving delta again. And again, for this delta is equal to a quarter, this will hold true. So there will exist an x and a y in the domain, so in the closed bounded interval AB, such that the difference between x and y, and the modulus of that difference, is less than a quarter, but the modulus of the difference between their image points is greater than or equal to epsilon bar. So again, this holds true. So if you put in 3 here, this is going to hold true. In fact, it holds true for 1, 2, 3, and it's going to hold true for all of the terms of my sequence onwards. So we're going to continue this on. So we'll next have delta is equal to 1/8, delta is equal to 1/16. For the fifth one, delta is equal to 1/32. We'll continue halving each time, and every single one of them you will be able to do, because this holds true for every single delta, that you can find 2 points x and y in the domain such that this holds true. So for the general nth terms in these two sequences, your delta will now equal 1 divided by 2 to the power of n minus 1. So it's not quite 2 to the power of n. As you can see, when we had 1, it was actually 2 to the power of 0. When we looked at the second term, it was actually 2 to the power of 1. When we looked at the third terms, it was 2 to the power of 2. So it's actually 2 to the power of n minus 1. So you'll look at this delta, and for every single one of these, it's going to hold true. So you can use this delta, and you'll be able to find 2 points in the domain such that the modulus of the difference is less than this delta, but the modulus of the difference between their image points is greater than or equal to epsilon bar. So this is going to hold true for all of these paired terms in these two sequences forever and ever and ever. So you can continue this on forever and ever and ever to produce infinite sequences. So how are we going to use these two sequences to arrive at a contradiction? Well, we're going to apply the Bolzano-Weierstrass theorem. So we actually only need to apply it to one of the sequences, and we'll choose the top sequence, the x sequence. So all of these terms in this sequence are inside this closed bounded interval AB, hence this sequence is bounded above and below, and therefore obeys the Bolzano-Weierstrass theorem that there will exist a convergence subsequence. So I have denoted this convergence subsequence xni. So this xn was denoting the original sequence. This is now denoting the subsequence, because this I index will run from 1, 2, 3, etc., all the way up the natural numbers, and n1 will be the first term of the original sequence that is included in the subsequence. So for instance, n1 might be 3, meaning that this third term is the first term of the original sequence that is actually included in the subsequence, so these two terms have gone. And then xn2 will be the second term of the original sequence that is included in the subsequence. So n2 will be some index in the original sequence, so it might be 6, let's say. So x6 would then be the second term included in the subsequence. n3, n4, n5, they're all the indexes of the terms that are being included from the original sequence in the subsequence. So this is how we'll denote our subsequence xni, and it's going to converge to some value, and we'll call that limit, we'll call it x. Now, x is guaranteed to be in your interval AB, because it cannot be outside of it. If you imagine, for the sake of argument, imagine it was outside of this interval, so it was somewhere up here, let's say. How on earth can this sequence, which is made up of things entirely in this closed bounded interval, be converging to something up here? There is a finite difference between that and this value b, and the terms of that sequence are never going to get within that distance, because they're never going to get greater than b. So it can't be the case that they are getting and getting indefinitely close to something that is outside of this interval. That's why it's crucial, actually, that we're dealing with a closed interval. This is where the proof fails for open intervals, because in an open interval, they can be converging to something outside of the domain. They can be converging to that boundary point that isn't included. So it's crucial that we're dealing with a closed interval here, and that allows us to conclude that the thing that this subsequence is converging to, this value x, is somewhere inside our domain. So if you look at the terms of this subsequence, I've circled them in blue here, just for sake of examples. These I'm saying are representing some of the terms from the original sequence that are included in the subsequence. So as we said previously, here is x3, the first term of the original sequence that's actually included in the subsequence, and so on. Now, every single one of these terms of this subsequence has a corresponding term in the y sequence. So x3 has the corresponding y3, this one has this corresponding one, this one has this corresponding one. So we can consider this subsequence of y, which is made up of the corresponding terms. So it would be the subsequence that we denote y n sub I. So remember, n sub I runs from 1, 2, 3, 4, 5, etc. And it gives you the indexes from the original sequence that you want included in the subsequence. So this will give us the same corresponding terms as we had in this subsequence. So m1, for example, was 3, so it'll be 3 here as well, so you'll get y3 as the first term of the subsequence. n2 might be 6, for example. n2 here will be 6 as well, so you'll get the corresponding term. Now my claim then is that this subsequence of y, which is the corresponding subsequence to this subsequence of x that converges to x, that this converges to this same limit that we're calling this point x. So why is that the case? Well, it is in fact just algebra of limits. So if you consider the limit as I approaches infinity of the difference between the two subsequences, so the y subsequence minus the x subsequence, that's going to be 0. Why is that the case? Well, it's because of the way the delta value gets smaller and smaller and smaller, in fact getting indefinitely small. So remember, the way that we chose these points, these x and these y terms for the sequence, these corresponding paired terms, is that they are a distance apart less than delta, and that delta as you go on and on is getting indefinitely small. So it is going to be true that the difference between these two values is going to get and stay indefinitely close to 0 as I goes to infinity. So yes, this limit is going to be equal to 0. We also know that the limit as I approaches infinity of this subsequence is this value x. So what we can now do is add those two limits together and apply the algebra of limits. So what I have now done is I've added the limit as I approaches infinity of the x subsequence to both sides. Now on this side I've just evaluated that limit, and its limit is of course x, so I've written the value x there. On this side, what we're going to do is we're going to use the algebra of limits to combine these two together, and we'll get the limit as I approaches infinity of the y subsequence minus the x subsequence plus the x subsequence. And of course, the minus and the plus will cancel, so we'll just get that the limit as I approaches infinity of the y subsequence is equal to x. Hence, the corresponding y subsequence does also converge to this value x that is somewhere inside our closed bounded interval AB. But here's the problem with this, because we now have these two domain sequences that are both converging to this value x that is in our domain. So here's a picture. Let this be the value x. So this sequence converges into this. This domain sequence also converges into this. So it should therefore be the case, because this function is continuous everywhere over the domain, it's going to be continuous at this point x. So it should be the case that the corresponding image sequences to these two domain sequences should both converge to the value of f of x. But why is that not going to be possible? Because of this criterion here that applied to the original sequence but also holds true for the subsequences, that the difference between their image values, the modulus of that difference, is always greater than or equal to epsilon bar. So it can't be the case then that both of these image sequences get and stay indefinitely close to this value f of x. Otherwise it will break this thing that we know is true. This is the way, after all, that we set up these sequences. So to say that again, the domain sequence for the subsequence of x, which is this, is going to have to converge to f of x by continuity, because this converges to x, and the domain sequence for the y subsequence, which is denoted by this, is also going to have to converge to f of x by continuity. But this is a problem because of this, and I've changed this criterion actually. I've changed this to n so that it is more consistent with what we've been using here, because we've been denoting these indexes n, and then the I has been denoting the subsequence index. So if these two are both converging to this, then that means that they get and stay indefinitely close to this value. So that means that you will be able to find an I such that both of these two are inside, for instance, an epsilon over 2 size interval around f of x, and therefore if you look at the difference between them, it's going to be less than size epsilon bar. Sorry, I said epsilon, I meant epsilon bar. If you would be able to find an I here such that both of these are inside an epsilon bar over 2 interval around f of x, and then if you were to think about what the difference between the two is, well, it's going to be less than epsilon bar, which would break this criterion, because for all n, the difference between, the modulus of the difference between these two has to be greater than or equal to that epsilon bar. So this is a contradiction, and hence we have proven that this original assumption that we had here, that uniform continuity was not satisfied, cannot have been true, because if it were true, all of this would follow, and it leads to a contradiction. Hence the opposite must have been true, so the actual uniform continuity criterion must have been true. Hence we know then that one of these beautiful functions that is continuous everywhere over a closed bounded interval does in fact obey the uniform continuity property. So it's not just continuous everywhere over that interval, but it's also uniformly continuous everywhere over that interval. And crucially, it relies upon that interval being a closed interval. It does not hold true, as we saw in the previous part with that counterexample, for functions that are continuous everywhere over an open interval. And the way the proof would fail is that we wouldn't have been able to conclude that this thing that they're converging to was actually inside the interval. So we'll end there. Thank you for watching.